The distant and jumbling area of Pluto was once named a genuine planet inside our planetary gathering. Anyway, ongoing discussions among leading astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have pushed Pluto back into the spotlight. Their urgent speculations suggest that Pluto might be on a potential collision course with Neptune, an idea that raises various questions. How could such an event occur? What might be the repercussions of such a tremendous impact? Are we witnessing a captivating, boundless anomaly, or is there a deeper, more complicated phenomenon at play? Join us as we examine the potential outcomes of a Pluto-Neptune crash. Once seen as a smaller and more distant member of the solar system, Pluto continues to captivate scientific interest and scrutiny. Leading investigations from top experts reveal that Pluto's orbit is perilously close to Neptune's, and several astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about a potential catastrophic collision between the two. Could such an event pose a significant threat to Earth? How would it unfold? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an extraordinary 248 years to complete a single revolution. Since its discovery in 1930, Pluto has not yet completed one full revolution. However, this is only the beginning of its intrigue. Pluto's orbit is highly elongated, in stark contrast to the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination of 17 degrees relative to the ecliptic plane, making it one of the most tilted orbits in the solar system. This inclination, combined with its irregular shape, adds to the complexity of its path through space. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For roughly 20 years during each cycle, Pluto actually travels closer to the Sun than Neptune. This challenges assumptions based on the relative positions of the two planets and naturally leads to the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery, with astronomers initially attempting to understand its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out due to its extreme tilt and irregular shape. The mystery surrounding Pluto's orbit crossing Neptune's is linked to the stability of its path, governed by a phenomenon known as the three-body problem. This problem seeks to understand how three celestial bodies, such as Pluto, Neptune, and the Sun, interact and influence each other's motion through gravitational forces. For Pluto, the three-body problem reveals how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex and balanced way. Terms like asymmetric libration, degree libration, and VZK wobbling are key components of this intricate problem. Astrophysicists explain that planets remain in their orbits due to a type of libration. For Pluto and Neptune, this term refers to the fact that whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune's position, preventing a direct collision. Degree libration refers to the oscillation of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune, it is positioned either far above or below Neptune's orbital plane, further protecting against potential collisions. Another critical element contributing to this stability is VZK wobbling, named after the scientist who studied how celestial objects move in space. This phenomenon explains how Pluto, Neptune, and the Sun influence each other's movements through gravitational forces, helping us understand why Pluto's path remains stable over long periods. Despite stabilizing mechanisms like asymmetric libration and degree libration, Pluto's orbit can still be highly unpredictable. Even the smallest changes in Pluto's initial position or speed can cause its orbit to evolve chaotically over time. Yet, despite this apparent chaos, Pluto's orbit has remained remarkably stable over billions of years, suggesting an underlying order in its journey around the Sun. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of our solar system. It shows how the positions and movements of individual planets can have far-reaching implications. While much progress has been made in understanding space, Pluto's case highlights how much more remains to be discovered. Numerical simulations conducted in the late 1980s revealed that, despite stabilizing factors, Pluto's orbit can be highly chaotic. Small variations in initial conditions can lead to massive differences over long periods. However, these anomalies have not disrupted Pluto's orbit, which has remained stable over vast stretches of time. Recent computational insights have provided further clarity on how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. For instance, Neptune and Pluto are in a unique resonance. For every 2 orbits Pluto completes, Neptune completes 3. This resonance stabilizes Pluto's orbit. However, Neptune isn't the only force at work. Jupiter's gravity also plays a crucial role in maintaining Pluto's trajectory, as does Saturn. These simulations suggest that Jupiter's gravitational force alone is strong enough to keep Pluto on a stable path for billions of years, potentially even indefinitely. The combined effect of Neptune, Jupiter, and Saturn is crucial in ensuring Pluto can traverse space without experiencing significant disruptions. These findings are essential for understanding the broader dynamics of the universe. Without such stabilizing forces, the solar system would be far more chaotic and unstable. Objects like Pluto could potentially collide with other celestial bodies or be ejected from their orbits, causing a cascade of disruptions throughout the solar system. In Pluto's case, understanding its orbit is particularly important considering ongoing discussions about a potential future collision with Neptune. Such considerations offer a clearer understanding of the dynamic nature of our solar system. Pluto's model demonstrates how even seemingly unstable orbits can achieve a state of balance through the intricate interplay of gravitational forces and orbital mechanics. This underscores the importance of continuous research to expand our understanding of our place in the universe. Exploring the vastness of space often requires confronting the unpredictability of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The concept of orbital resonance, which refers to the delicate balance of a celestial body's orbit based on its initial conditions, is clearly demonstrated by Pluto. Even minor variations in Pluto's position or speed can significantly alter its long-term orbital trajectory. Simulations have been instrumental in studying how Pluto moves through space. These simulations use complex mathematics to model the gravitational interactions among Pluto and other celestial bodies, such as Neptune. By altering small details in these models, astronomers can observe how even minute changes can lead to dramatic shifts in Pluto's future path. Despite the stabilizing mechanisms like asymmetric libration and degree libration, its orbit remains highly irregular. Yet, over billions of years, Pluto has maintained remarkable stability, suggesting that an underlying order governs its motion. The eccentricity of large orbits like Pluto's presents significant challenges for astronomers. The inherent nature of these systems suggests that long-term predictions are often fraught with uncertainty. While numerical simulations are powerful tools for understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of such forecasts. These models heavily rely on the accuracy of initial conditions and the complexity of the interactions they simulate. Even a slight error in these conditions can dramatically alter the predicted outcome, making accurate predictions incredibly difficult. Moreover, the chaotic nature of vast orbits like Pluto's serves as a reminder of the constantly evolving and dynamic nature of the universe. While significant strides have been made in understanding the cosmos, Pluto's case underscores how much more remains to be discovered. By studying the gravitational effects of giant planets on Pluto's orbit, astronomers gain valuable insights into the broader dynamics of our solar system. This illustrates how the positions and movements of individual planets can have sweeping ramifications, highlighting the delicate balance that governs celestial mechanics and its impact on the stability and trajectory of various objects in the system. This brings up a crucial question. Why are prominent astrophysicists now expressing concerns about a possible collision between Pluto and Neptune, despite the many complex forces at play to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist, offers a detailed perspective on the mysteries of our solar system, particularly through the intriguing example of Pluto. Tyson, who played a significant role in reclassifying Pluto from a planet to a dwarf planet, provides a thoughtful analysis of the evolving nature of celestial mechanics and the growing public interest in the distant corners of space. According to Tyson, the renaming of Pluto was not a demotion but rather a necessary change reflecting our expanding understanding of the various bodies orbiting our Sun. Tyson views the complexities of Pluto's orbit and its interactions with Neptune as a reflection of the unpredictability of space. While he acknowledges that Pluto's orbit is stable for now, he suggests it could undergo significant changes in the future. This possibility has raised questions about the future of Pluto's path and the potential risks it poses to the solar system. As we continue to explore the intricacies of Pluto's orbit and the forces that govern it, the mysteries of the outer solar system remain an exciting and crucial area of scientific inquiry. The conversation surrounding Pluto, its orbit, and its possible interaction with Neptune illustrates the complexities of our cosmic neighborhood and the importance of ongoing research in understanding the dynamic nature of the universe. As scientists delve deeper into the intricate mechanics of Pluto's orbit, they are forced to confront the uncertainty of celestial dynamics. The possibility that Pluto's orbit might not remain as stable as it appears raises critical questions for the future of the solar system. If Pluto's path were to change dramatically, especially in relation to Neptune, it could have profound implications not just for Pluto itself, but also for the other objects in the Kuiper Belt and beyond. The consequences of a collision between Pluto and Neptune, although unlikely, are so vast and unpredictable that they demand careful attention from the scientific community. Moreover, the study of Pluto serves as an important reminder of how little we truly know about the farthest reaches of the solar system. Despite the significant progress in our understanding of planetary motions and orbital mechanics, many aspects of our solar system remain shrouded in mystery. Pluto's complex orbit and its potential interactions with Neptune exemplify how unpredictable these distant objects can be. This sense of uncertainty fuels scientific curiosity, prompting astronomers to continue developing new models and conducting simulations to test different scenarios and outcomes. The growing focus on Pluto and its relationship with Neptune highlights an essential truth in astrophysics. The universe is not a static system, but a dynamic and ever-evolving one. Even with the stability observed in Pluto's orbit over billions of years, the possibility of sudden shifts or unexpected interactions cannot be ruled out. These potential changes, although subtle, could dramatically alter the course of celestial objects and influence the structure of our solar system in ways we cannot yet fully predict. As we continue to explore the outer regions of the solar system, the case of Pluto reminds us of the importance of continued observation and research. The tools and methods used to study these distant objects are constantly improving, allowing for more accurate simulations and deeper insights into the forces at work. Understanding the behavior of Pluto, Neptune, and other distant bodies will not only shed light on the past and present of our solar system but also help us prepare for the future. In conclusion, Pluto's journey through space remains a fascinating and complex subject for study. Despite its reclassification as a dwarf planet, it continues to captivate scientists and the public alike. Its orbit, while currently stable, serves as a reminder of the dynamic nature of the cosmos and the ever-present possibility for change. Whether or not Pluto and Neptune will collide remains uncertain, but the investigation into the forces that govern their paths will undoubtedly lead to new discoveries that deepen our understanding of the universe. As we continue to probe the mysteries of space, Pluto's place in the solar system offers valuable lessons on the importance of exploration, curiosity, and the unyielding pursuit of knowledge.